So welcome back, students, and with this video we start introduction to the theoretical concept of georeferencing and map transformation. So let's start. So the first question you can ask: why we need georeferencing? GIS and remote sensing specialists work with various types of spatial data. This can be aerial images or drone images, like this oblique aerial image of the terrain, or raw satellite images like Landsat and Sentinel, or old maps without coordinates like this old map of Italy. So if the map has coordinate system, it can be reprojected to another coordinate system, like the map of India, which is on the left side, which has the coordinates of EPSG 5837, which is reprojected to another coordinate system of EPSG 4326. But what if it doesn't have any coordinate system, like this old map of Great Britain and Ireland, which is drawn by hand several centuries ago, when people didn't have computers. And here starts the concept of georeferencing when we need it. So coordinates of a newly digitized map are represented by digitizer units from a point of reference on a sheet of paper, or coordinates of an image are represented by column and row pixel indexes. You have to georeference a digitized map or image to a map projected coordinate system in order to use this data in GIS analysis. Like here, for instance, we can see the image of, on the left side, a pixel image, which has columns and rows, and display units are pixels. And on the right side, we see the same image, which is georeferenced to a map coordinate system with units of meters, feet, etc. So the overall procedure of georeferencing, or in other words, image rectification, consists of 3 steps. The first step is image registration, the second step is geometric transformation, and the third step is resampling. And we focus on each of them on the following slides. So the first step is image registration. Image registration refers to the process of the identification of corresponding points in an input image and a reference dataset in a known map projection. These points are called ground control points. Like on the both images below, we can see the first is reference map and the second one is image. The first one is also image called the master map, the master image or master map, and the second one is called the slave image because it doesn't have the coordinate system. And we should find, the first step is we should find the same locations. We should identify the same locations and objects on both images and refer the second image to the first image. And these locations are called ground control points. So the second one is geometric transformation. The control points are used to determine the coefficients for 2 polynomial transformation functions that describes relationship between image coordinates and map coordinates. So here we can see the concept when the xy map coordinates, xy with the letter and are referred to x input image coordinates, columns and rows, with the transformation equations. So when you find the locations, when you identify the ground control points on both images, ArcGIS automatically creates a function which makes a relationship between referencing between the slave image to the master image. Once the coefficients for these transformation functions are determined, the image coordinates for any set of map projected coordinates can be estimated. A common transformation is the first order linear affine transformation. So there are three types of the geometric transformations. The first order polynomial equation is called affine transformation. The second order also we have, and the third order. For the first order type of polynomial transformation, we should find at least 3 ground control points, but preferably to find more, for instance 4 or 5. For the second one, we should identify at least 6 ground control points on both images, but preferably 7 or 8. And for the third polynomial, we should identify at least 12 ground control points. So the third step is resampling. During georeferencing, a matrix of empty cells is computed using the map coordinates. Then each empty cell of the output raster is given the value of the corresponding cell, determined by the transformation function, or cells in the input image, based on a process called resampling. The two most common resampling techniques are the nearest neighbor assignment and bilinear interpolation. These techniques assign a value to each empty cell by examining the cell values in the unreferenced raster dataset, the input image. A third common resampling technique is cubic convolution. So we at first let's consider the nearest neighbor technique. So nearest neighbor assignment is the fastest resampling technique and is appropriate for categorical or thematic data, since it does not alter the value of the input cells. Once the location of the cell center on the output raster dataset is located on the input raster, nearest neighbor assignment determines the location of the closest cell center on the input raster and assigns the value of that cell to the cell on the output raster. The nearest neighbor assignment does not change any of the values of cells from the input raster dataset. The value 2 in the input raster will always be the value 2 in the output raster. It will be never 2.2 or 3. Since the output cell values remain the same, the nearest neighbor assignment should be used for nominal or ordinal data, where each value represents a class, member, or classification. This may be categorical data such as land use, soil or forest type. So on the image below, we can see the concept of nearest neighbor when the closest sorry, that was the wrong image. Here is the actual nearest neighbor technique image. Here we can see the output with blue color output raster image, and with the black color input image. Here is a cell center, and those input pixel which has the more overlapping with the output is given the value to the output pixel. So the second one is bilinear interpolation. Bilinear interpolation uses the value of the 4 nearest input cell centers to determine the value of the output raster. The new value for the output cell is the weighted average of these 4 values, adjusted to account for their distance from the center of the output cell in the input raster. This interpolation method results in a smoother looking surface than can be obtained using nearest neighbor. So if we mostly use nearest neighbor for the discrete rasters, like for instance land use cover, soil types, etc. Bilinear interpolation and later on the cubic convolution is used for mostly continuous rasters, because they they take as an input of values of the 4 input pixels and give the output cell a weighted average of these 4 values, adjusted to account for the distance from the center of the cell, and also the overlaying of overlaying territory. So since the values for the output cells are calculated according to the relative position and the value of the input cells, bilinear interpolation is preferred for data where the location from a known point or phenomenon determines the value assigned to the cell. That is, continuous surfaces, elevation, slope, intensity of noise from an airport, and salinity of the groundwater near an estuary are all phenomena represented as a continuous surfaces and are most appropriately resampled using bilinear interpolation. And the last one is of resampling technique is the cubic convolution. Cubic convolution is similar to bilinear interpolation, except the weighted average is calculated from the 16 nearest input cells, centers, and their values. Cubic convolution tends to sharpen the data more than bilinear interpolation, since more cells are involved in the calculation of the output value. Therefore, this resampling method is often used when resampling imagery such as aerial photography and satellite imagery. So cubic convolution mostly used during the using of high spatial resolution input raster. For instance, it's mostly drone images, aerial images, or high resolution satellite images, and where the pixel array is small, and we can use 16 input pixels, nearest pixels, to resample our aerial image. So here is the image of how the cubic convolution works. So 16 pixels are taken into account, and the average, so the weighted average is calculated from the 16 input cells and their values. So from this from this slide, the lecture ends, and we will work on the georeferencing during our practical tutorial, and mostly we will test nearest neighbor and also bilinear interpolation. Cubic convolution is out of the scope of this course, and mostly they are used with the GIS professionals during the resampling of aerial images.